Communitech Data Hub, and welcome to our online viewers as well. I think we're going to get started. Before we begin, my name is Kusha, and I work with Communitech, and I'd like to thank the City of Waterloo for sponsoring today's event, and I'd also like to thank CIBC for presenting. As you may know, the CIBC Data Studio is based right here out of the hub, and they're also hiring for full-time and co-op data science positions. So if you're interested, please find us after the event and let us know. I'm pleased to introduce today's speaker. Dr. Kuhan Wang is a senior research scientist at CIBC. He began his career working on particle physics problems at CERN through the ATLAS Collaboration Project. He led data analysis efforts in finding new physical phenomenon using massive amounts of data that came out of the Large Hadron Collider. Later on, he became a data scientist in New York City, solving natural language processing problems, developing the statistical frameworks for various projects, and implementing production AI models for Gartner. He's working currently on applied machine learning problems in finance and banking. He holds a PhD from McGill University and an MSc from the University of Victoria, both in experimental physics. Welcome, Dr. Kuhan Wang.
Hey, can you guys hear me okay? Well, first of all, thanks for that very generous introduction. So I began my career sort of as a physicist, so I was not trained as a computer scientist. So sort of like I came into this kind of from an experiential point of view. So first sort of learning the heuristics and applications, and later on I sort of got more interested in the theory and the machine learning side of things. So today I'm going to talk to you guys about this idea of vector embedding, which is it's a relatively new sort of thing that came along about 5-6 years ago. That was the first paper came out on Google. And hopefully by the end of it, I'll convince you that it's a very useful application in a lot of machine learning problems. So here's the sort of the table of contents of what I'll talk about. So, maybe we'll talk a little bit about neural networks as an introduction very quickly. And then we'll talk about word embeddings in unsupervised learning environments. And then after that, we'll talk a little bit about how you could sort of leverage vector embedding models in supervised learning as well. So usually in academic talk, you kind of sort of like talk for 20 minutes about the theory of stuff, and then by the end, when nobody's listening anymore, you actually get to the point. So I'll just start with the point right at the beginning. So vector embedding is basically, if you can think of it as like an intelligent way of converting categorical entities into real vectors, right? So you could think of like the simplest way to do that is to one-hot encode, but it turns out there's much smarter ways we can do this that sort of, as we'll see later on, sort of reveals the hidden structure of the variables themselves. So here's one where it was trained, this is a word-to-vec model that was trained on the Bible, so you can see basically, you categorize certain entities in the Bible together. So you got like the 10 plagues, you got the Exodus, you got aspects of the Trinity. So basically, the idea is, like certain words like famine and pestilence, these are close together, and then that's further away from words like Peter, right? So this is kind of like the payoff. This is like at the end of all your hard work, here's what you get, and this is great. So how does that actually work? So maybe first of all here, so we'll just do neural networks in 3 slides really fast for anybody who doesn't come from the field. So you can imagine like the simplest machine learning problem you can think of, right? It's not even a machine learning problem. It's just you have a bunch of points and you want to fit it to a line. And if you only have one dimension in your input, that would just be like, in high school when you drew a bunch of dots on a curve and then you took a ruler and then drew a line through it, right? If you had multiple sort of features or multiple variables, then you would be doing multivariate regression. And then if you got really fancy, you could have then, instead of doing linear regression, you can fit like a curved line to it. So in this case, it'd be logistic regression, right? And so that's kind of like the simplest, most interpretable machine learning model you can build, which is a logistic regression model. You have some input variables and you have some target variables, and then you're trying to learn basically a mapping between them. So what if I just, instead of having like, one logistic regressor, I just stack multiple logistic regressors together, right? So for instance, you can imagine that I have some input and then it goes through a logistic regression, and then after that, I take the output of the logistic regression, which would normally have been what I was trying to predict, and then I put that as the input into another logistic regression and then get the output of that. So, and that is essentially what a neural network is. A neural network is basically stacking logistic regressions. Now, there's some complications because you might not necessarily use a logistic regression inside each of these neurons. You could have, there's like nowadays, there's fancier ways of doing it. But this is basically the simple, straightforward idea of a neural network that you can sort of interpret, intuitively understand, which is sort of just stacking logistic regressors together. And then deep learning literally just means stacking more layers of logistic regressions together, right? So if you have more than one hidden layer, so a hidden layer is any layer that's not the input or the output, then you can call yourself a deep learning practitioner. Okay, so that was neural networks in 3 slides. Okay, let's talk about Word2Vec then. So we go back to what we were talking about all the way in the beginning. So what's going on in a neural network model is that it's basically, Word2Vec is a very specific application of vector embedding to natural language, and this is like a really good starting off point because the results are very, very spectacular and good. And so it sort of like drives the entire conversation about vector embedding. So imagine you sort of have, you know, like a corpus. So you have a bunch of documents, and there's words in the documents, and it's human readable. So you have like sentences in them, like I like playing football with my friends, and maybe some other sentences to forward on. Basically, the idea of Word2Vec is that you take a sliding window across your words from left to right, like you would read them, and then you try to basically, in each window, you look at sort of the center word and then the words around it, which we call the context words, and you're trying to learn out of all the words in a dictionary, which is so all the words in your sort of corpus, what are the words that sort of match, right? And the way to see this is, so in this case, it would be like the center word in the second one would be like, so it would be what is the words that are associated with like, or in the context of like. It would be like I playing and football, but it would not be with and my and friends, right? And then you sort of move the window over and over and over. So the underlying algorithm, what it's trying to do is basically, it's trying to maximize the co-occurrence of specific word context combinations. So this is kind of like the underlying formula. This is probably like the only formula. I'll try my best not to show too many formulas today that you sort of have to sort of get at the high level, which is essentially you have an output word and an input word. So the input word would be like your context word, and then your output word would be the middle word. And you're trying to basically then do this operation. This is called a softmax function. And the idea is that these news, these Greek news, these are what you're trying to learn. These are the vectors, and these are real numbers, or vectors are real numbers. So you can imagine, for instance, they could be a size 10 or 100. These are kind of actually arbitrarily defined. And you basically, the idea is that you move these numbers around in such a way that you make this probability as large as possible given the training data, right? So the idea is basically you want to maximize this for all the true combinations of word contexts. And so the bottom term really here is a normalization. So it's for that particular context, what's the probability of that over the probability of all the possible contexts you can make, right? And feel free to stop me at any point if there's any questions. Hey.
So, sorry, what was the input word and what was the output word?
So the input word in this case would be, so if you take like, it's kind of like, it's easier to understand if we sort of like go right into the middle instead of like on the side, right? So if you look at this sentence right here, the middle word would be football, and then the context word could be any of those 4 words, right? Whereas the entire vocabulary would be all the words, right? So then if in this formulation, we should assign a high probability that football and playing go together, but football and friends don't go together, right? Because friends falls out of the window,
Okay, so football
right?
could be the input word.
Yeah, so football will be the input word at one point, and it will also be the context word in another point, right? Once we slide the window one more word over, right? So each word will actually take both places, as a context and as a target word. Okay, so that's cool. So if I take this and I try to really break it down, right? Because if you're like me, you don't really understand unless you sort of work out the algebra, right? So this is a function, like an equation representation of this, which is the actual neural network. So if we actually break down this neural network in terms of a series of matrix multiplications, what is actually going on, right? So here, each of your words in your vocabulary, so you have 1, 2, 3, 4, 5, 6, 7 unique words in your vocabulary, is one hot encoded as, you know, as basically a 7-digit or 7-element vector, and so are your context words. So what's really going on in this equation if we break it down, right? So if we look at it here, what it is, so on the left-hand side, you have your one-hot representations of your target words, right? So here, let's just take an example. We'll say we have 4 words in our vocabulary. So your one-hot vectors have 4 elements in it. And then let's just say we only have 3 training examples. So it's a really, really small corpus that we have, right? So this is the input, and then this here is your embedding matrix. So the embedding matrix, obviously to do a matrix multiplication, the number of rows here has to match the number of columns here, right? So that means that there's going to be 4 columns here, 1 for each of your vocabulary words, whatever they may be. And then this, the width of this matrix is called the size of your embedding, and this is arbitrarily sort of, this is like a hyperparameter of your model, essentially, you can tune. And so if you actually try to do this matrix multiplication, you basically realize what it's doing in this first layer is that this matrix multiplication is literally just picking out columns of this matrix, right? So so if you do the first one's going to come out, it's going to give you ABC, and then it's going to give you DEF, right? So this matrix here of 3 by 4, this is the embedding matrix, and basically the values of A to E are what you're trying to learn when you're saying, I'm training a word-to-vec model. And then what happens next is then, okay, so we do that matrix math, we do that product, and then we get, you know, J to JKL, that's going to be the first row, the DEF and ABC. And then we multiply that by your softmax layer, right? So that's just basically now doing this multiplication here of new transpose to new. And if we do that then, which is the hidden layer, so this is the embedding layer, which we pass to this, which is we call the softmax layer, we get what we get is essentially this. So this is basically what was shown on that page. So for every single one of these elements, we are taking the exponent, and then we're dividing by this normalization, which is essentially saying to us, what is the probability that that particular target word goes with all the possible words in our vocabulary. Now, so in this case, there's only 4 words in our vocabulary, right? So each of this is essentially like a ratio of what's the probability of this target with that word, then with this word, and then that word, all divided by different probabilities. And so it took me like 20 minutes to, you know, write this out on a piece of paper. And so you can imagine in a real corpus, actually, with like millions of words, this is actually very expensive, even for a computer to process. Even on a GPU, this would be very expensive. And it's basically because this sum is over all the possible words in your vocabulary. So in real life, in practice, vector embedding algorithms are typically trained using some kind of like approximation or some kind of heuristic. So we won't try to actually optimize the entire softmax. We'll try to find some trick to basically do it in a way that is not completely correct, but is much, much, much faster. So there's a bunch of these algorithms that exist, and I won't go into them in specific detail unless, you know, somebody asks. But the basic idea of a lot of them is that instead of, because the part that slows you down is essentially having to come up with this normalization, which is summed over all your vocabulary terms. Instead, you just pick a few, randomly pick a few out of the entire bucket of vocabulary terms and compare it to your current context. And then you train that sort of as like a supervised classifier, and that's usually how we do it in life. So in this first particular case, right, you would just train, you would say, this would be your context, so the quick brown fox jumps over the lazy dog. So D and quick, you would say, well, is that correct? Or is D and fox correct? Or is D and jumps correct? So there's only one correct one, which is D and quick, right? And then you sort of do it this way as sort of as pairwise training, as opposed to trying to evaluate over the entire corpus. And then the actual training, there's many different ways we can do it. So we can do it using gradient descent or some other algorithm like AdaGrad or Atom. I mean, we can even use Newton's method. Yep.
In the previous example, the window size is 2.
The window size here is 5. Well, the window is 5, but it's just like when you're at the beginning, the window is only one-sided. So there's no pad, right? Because at the beginning on the first, so this is the full size when you see the quick brown fox jumps, but then at the very beginning there's just no words to the left of it, right? So
These different algorithms, the window size matters?
yes, the window size matters. So you can sort of imagine if the window size grew, well, so the size of the window is capturing how big of a context you want, right? So when your window size is small, you're sort of capturing the local similarity of the word with the context. And then as it gets bigger and bigger and bigger, you're capturing more and more global similarity until the point, if you were to take it to its logical conclusion, the window size was the size of the document, you would essentially be learning how similar is this word to all the other words in the document, right? And also your computational complexity grows rapidly because you have to sample more as your window size grows. So that's also sort of a hyperparameter of your model that you have to control for.
Is it a result for which algorithm is best for the maximum window size? Let's say, with your example, if the window size is the whole document, what's the best algorithm?
So if the window size was the whole document, I don't think you would actually learn anything because every word, basically the context for every word would not really be unique, right? See what I mean? Like if you have 2 words and 2 sentences and the 2 sentences were adjacent to one another, if the window size was 1, these 2 words would have unique contexts, right? So they would learn unique definitions. But if the window size was the whole page, then for the most part, their context is identical, right? So then I'm not sure what you would exactly learn in that situation. So I don't think you want it to be that big.
I will just exaggerate. What I'm saying is, let's say the window size is half the document. What is the best algorithm for this situation? Is there any result for that?
Oh, you mean like, which are these like approximate algorithms? So I think they're all these algorithms do not determine the quality. They just determine the speed at which you train. Right. Okay. So like here will be the example. So in this particular example, this was not particularly for Word2Vec training. I just pulled this off Google Images. So basically, if you were thinking of this as Word2Vec, these would be like dimensions of your embedding size. So in this example, literally your embedding size would be 2. So you couldn't learn very much out of it. And then this would essentially be your loss. So that would have been your softmax probability that we saw a couple slides ago. And this is like, so gradient descent is not really too far off from what we learned in high school. Newton's method, calculate the derivative and just go down the slope, and eventually hope you hit somewhere with low loss.
Question?
Yep.
So from your diagram there, and I know it's just an example, but I mean, it looks to me like that other purple trough could be lower. So
Yep.
The point is, does it suffer from
Yeah.
local minima problems and this kind of stuff?
Yeah. So it turns out actually like in a deep neural network, this is as far as I know, I'm not a computer science expert, but in a deep neural network, the more layers you have, the sort of more local minimums you have, and it's harder and harder to find a global minimum. But it turns out it doesn't matter because all the local minimums are just about as good. So that's kind of that's something to. It's kind of like a quirk that just works out through the mathematics. But that being said, Word2Vec is actually like a 1-layer neural network, so it's not really deep learning. But in that case, then yeah, that's something you can play with. But usually you would sort of, when the embeddings are, when you first begin training, you don't initialize the embeddings at 0. You sort of initialize them randomly, and then that really helps define the good minimum. Yeah, and then the other. Well, yeah, maybe we'll talk about it. But it's yeah, because with language in particular, it's kind of hard to evaluate how good is one minimum next to another one. All right, so that's sort of like how you would train neural networks. So now you might like think to yourself, and I thought this too, like when I first saw this, and I was like, okay, this is kind of cool, but you know, how is this different than if I just like, I had some corpus, like say the corpus is I enjoy flying, I like NLP, and I like deep learning, and I just took all the unique words in it, and I just counted up how often a particular word occurred next to another word, right? And then I built this basically word co-occurrence matrix, right? So in this very small corpus, the word like appears twice to the word I. So that would be, you know, and then I just counted this up. And then afterwards, I just said, well, you know, I'll just say the most similar word to like is I because it occurs most frequently next to I. And then hopefully if I have a big enough corpus, how is that any different than what you have just done with all this complicated machinery, right? And so in the next couple of slides, I sort of hope to convince you that Word2Vec and vector embedding is a lot more than just doing these traditional methods, because essentially this is kind of just doing like some variation of TF-IDF without the normalization. So the first thing is co-occurrence is not the same thing as context, and you can sort of just imagine like a really simple thought experiment to tell you this. Basically, so imagine like you created a matrix like this for a whole stack of deep learning papers on sort of an archive. So never mind, you could even do that because you probably don't have enough RAM to fit the whole thing in memory. But if you could, then the model will tell you that deep is similar to learn and neural is similar to network, because neural network and deep learning, these words co-occur a lot, right? But neural and network, they co-occur, but they have no semantic relationship, right? Neural is not a synonym of network, whereas a vector embedding model would learn that difference. So basically what you have done is instead of building sort of like a synonym dictionary, which is sort of one application of Word2Vec, you've actually built a bigram detector. So it's also very useful because now you can scan through the whole sort of corpus and figure out what your bigrams are, right? So you can figure out neural network is actually one thing and not two things. And this is important actually as a pre-processing step to real Word2Vec models, where you would first pass the entire corpus through a bigram, maybe even a trigram, or you can keep going, detector, iteratively to basically enrich your vocabulary so that the ultimate size of your training vocabulary is actually bigger than your unique count of words, right? That's the other thing why, you know, sort of Word2Vec is very computationally intensive to train, because these vocabularies can easily, you know, exceed 1 million unique terms.
Wait, so
Well, that should happen naturally because you might have instances of the word neural showing up with not as part of the word neural network, right? So then you would still have the original term neural, and you would have the new term neural network. So, right, unless your corpus never had the word neural by itself.
So for further questions, I'm just going to toss the mic. So you can toss this mic, just so that our online streamers can also hear the questions.
So here's a couple other nuances of word embeddings that you will not ever get in a one-hot encoding or some kind of just co-occurrence frequency counting, essentially, right? So one, embeddings have compositionality. That's like a fancy way of saying that you can basically add and subtract words essentially in that embedded space and they would have meaning. So this is like a really cliched example at this point where basically, you know, you train a Word2Vec model and then you do king minus man and it gives you queen because it understands that, well, it takes away the, I guess what you would call them, the masculine part of the royalty indicator and it returns you the results, right? The other is that because you've now embedded it into a continuous real vector space, that means that you can interpolate, right? So that means that basically if you're somewhere between king and queen, it's some kind of like gender neutral meaning of royalty that we don't have a word for in the English language. And that would have been impossible if you just have the traditional categories that you started off with, right? And there's some learned understanding of grammar. So so words like ant and ants, they would appear similar in similar places, like walking and walked, swimming and swam. So this all kind of depends on what kind of corpus you train it on. So here is kind of like, I would consider the functional sort of flow chart of how you would train a Word2Vec model for actual applications, right? So the first question you got to ask yourself is, do you have a large corpus? If the answer is no, then don't train a word-to-vec model. Then you would, you clean, you generate your n-grams, and then you have to very carefully control your vocabulary, because if you were to take all the vocabulary terms, it's very likely that even on latest hardware, you would not be able to train a reasonable amount of time. So typically these are kind of done by doing some kind of like frequency analysis, where you just prune off like the words that occur the least 5% or 6%, or however you choose. And then you construct your vocabulary, which just means you map every single word to a term in the dictionary, 1, 2, 3, 4, 5, 6, 7, 8, so that what the model sees is not words, but actually just numbers. And then you train the neural network, right? So this box here is literally everything we just talked about up to this point. And then finally, this is like an additional step, is then you have these vectors. So maybe they'd be 100 dimensions or 200 dimensions, and then in a real-life task, you want to do fast lookup, so you would have some kind of like nearest neighbor algorithm that you would train on top of that to basically do that kind of fast lookup. So that's sort of like neural networks in a nutshell, but then now I'll run through some applications, and then we'll talk a bit about some more advanced application. Yeah.
Okay, hold on. Catch.
Oh, so that's why it's got styrofoam.
So I have a few questions. N-gram, N is the size of the window?
No, the n-gram is like the bigrams and the trigrams, and
N-gram means how many words?
how many of these linked terms do you want to come up with? So you would have to train so n-gram would be, say, bigram, that would be 2 gram, 3 gram is a trigram, and so forth. So
How many words you consider, yeah?
No. How many of these? So when you're training, because there's like a lot of combinations of words that have meaning, right? Like credit and card have meaning as one term, but credit and card by themselves have completely different meanings, right? So you would train sort of a co-occurrence model first to identify which words when fused together, have like an additional meaning, like credit card and neural network. Identify those sort of as a way to enrich your vocabulary, right? So now your vocabulary not only has the term credit and card, it's also got credit card as a separate word. And then you can also do that for 3 grams. So if there was like credit card Visa, that was like a term, then it would learn that as well, right? So first you would sort of do that kind of an activity to make your vocabulary richer and then you would train your word-to-vec model on all these terms. So you'd be training on credit, you'd be training on card, and you'd be training on credit card as an additional term. That's what is meant by n-grams.
Can you bring the last diagram? So here, n is a parameter, and then the heuristic that you use is another parameter. So if you vary this, you'll get like different results. So then how you compare which one is better?
So you have to evaluate them sort of using like a mechanical Turk, where you have to human evaluate for these kind of activities. Okay. Yeah. But we could talk more offline. So here's a real world example using in search engine query understanding. So basically in a search engine, you type in a query, like you type in big data, and then what it does is that instead of actually searching against big data, it will first do a query expansion and expand the term to data lake, data warehouse, machine learning, or any number of other synonyms, and then execute the search on each of them, then sort of merge and re-rank them, and then return the results, as opposed to just basically searching on big data, because it knows there's kind of like similar terms, and maybe you search big data, but actually you meant like data warehouse because you just didn't know what the term data warehouse is. So this is like an actual production example of where word2vec would be utilized to basically as a thesaurus for word lookups. Another one is sort of in product recommendations by looking at user histories. So this is an example where Yahoo, what they did is they look at your mailbox, and then they look at sort of purchases you have made, and then they recommend new purchase for you based on the sliding window of all the purchases you have made to basically generate product embeddings, right? So if you made a purchase of like a chair, and then afterwards you purchase a table, maybe you'll recommend the next thing you purchase is like a desk lamp, by sort of crawling over this many users. So these are two kind of possible use cases. So once you sort of have like word embeddings, there's actually something called there's a natural extension to this, which is document embeddings, right? So in your first case, you had your words, but your words didn't really have any global sense. Like this word comes from this document or this paragraph. This other word comes from this other document or this other paragraph. And you can incorporate that as a model called DocDevec, which basically then learns sort of on top of a word embedding, it learns a document embedding. So now you have a embedding vector for each word, but also in addition for each document. And once you have that, that's very powerful because in any kind of informational retrieval system, you now have like a quantitative description of every single document, and you can basically do sort of all sorts of traditional machine learning like clustering and similarity between documents, and you can just sort of see the use cases there in terms of, say, recommendation engine pipelines or sort of in search engines for informational retrieval. By doing doc-to-doc similarity in the exact same way you do word-to-word similarity. So that is, so DocDevec, that's an extension on top of word-to-vec. Yep.
So when you're training your word-to-vec, like, does word occurrences matter? Like how many times does the word occur?
No, so you don't have to do, well, they only matter in the sense that you would prune away the least frequent words to control your vocabulary, but you don't have to do any additional pre-processing on top of that before you train. So it's not like you have to lemmontize or you have to, or stem a word. You just sort of let it all go in because that's all part of the unique vocabulary and actually makes the outcome better and richer.
Okay, a follow-up question on that. So is there a scenario where that some words are learned properly and some words are not because of like number of times that
Yes,
they may occur?
yes. We can get to
How
that.
do we distinguish that?
So in the case of words, you would just have to look at them, right? So you would see sometimes that you would not learn a good synonym for a particular word because it was used in some funky, or like it was used in two very funky ways. But yeah, that can happen. Yes.
Okay, thanks.
Okay, gotta go a bit faster. All right, so graphical models. So this is sort of, once you sort of have this idea, okay, so in your head of word-to-vec, which is kind of like naturally intuitive because human language is intuitive to everybody, you can extend this concept of context to sort of arbitrary entities, right? And the easiest way to see this is you think of a document or like a sentence in an abstract sense, it's like a directed graph, right? So here's like a sentence from the New York Times. It starts here, the Trump administration will encourage this nation's schools to blah, 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 blah. And it's just, this is a very simple trivial graph, right? Where each node just points to the next node. There's no walk back, there's no recursion, and they all have weights of 1. So here's like a more complicated graph. This is the karate club graph, which is a graph of high school students who all belong to the same karate club. And here you can have, so each node here is a human, and then the connections are friendship between humans. So there's kind of like two cliques here, the blue and the red cliques. And then this graph is now no longer so simple, right? Because now each node can be connected to multiple nodes and sort of vice versa. So once you can do that, then you sort of, if for any kind of data which you can represent as a graph, you can now then model it as a word-to-vec, quote unquote, model, right? So here, basically you would just do an analogy. So the context here now is the node and is no longer, or sorry, the words are the nodes, right? And the context is basically some neighborhood of the node. So the way it's done in the deep walk, which is kind of like a seminal paper on this, is by basically doing random walks about each node, and that's basically your context. But the important thing to note here is then now, unlike in a sentence, each word, each target word no longer has a unique context, right? Each word, each node here now can have multiple non-unique contexts because I could sort of like walk here, but then I can walk another way, and then I would get two different contexts for the same node. And sort of in addition, in a graph, there's two types of similarity. The first type is the same as in a language and in words, which is that adjacent nodes are similar because they're basically connected to each other, right? There's a second case of similarity, which is that two nodes are similar because they have the same function in the graph, right? So here, 1 and 34 are similar, despite the fact they're not actually connected because they're both hubs in the graph, right? So that's a second sense of like global similarity. which can also be captured in these kind of models. So deep walk, in the deep walk model, where we only do random walks, we can only capture the first sense of similarity. There's additional, then after that, about later, people figured this out, and they came out with another paper. This was called Notivec, which basically makes the walk, effectively makes the walk go even further, go deeper, and then you can control how deep the walk goes to sort of get this macro sense of similarity. So here's an example I made. So this is a graph made by crawling URLs on the internet and sort of just then taking the domain names of the URLs and fusing them together. And then the connections, the edges here are basically meaning two domains are linked. They have a link between them. Right? So if you then try to run deep walk on this, what you would learn is sort of Facebook is similar to Twitter. The domain name Facebook is similar to Twitter, which is similar to LinkedIn, which is similar to Instagram, because they're all linked to each other. They sort of like form a little clique. And then Science Channel is similar to TLC, which is similar to Velocity, because they're all linked. So this is kind of like, so this is like a very straightforward application which you could do to, as a way of essentially, taking advantage of graphical data in a embedding model, using an exactly analogous sort of procedure to Word2Vec. So that's sort of like all I have to say about unsupervised learning. Supervised learning, that's the next part where we can sort of leverage Word2Vec models. So in the first case, so you can think of like, if you have a single categorical variable, let's call it x. So it's called cat x, right? And it's basically got a very trivial target. If x is odd, I'm going to just say the target is 0, and then if x is even, I'm going to say the target is 1, right? So if I asked you, all right, make a machine learning prediction, let's just say for some reason you want to do this and you just didn't know the answer, make a traditional machine learning algorithm that basically learns this target. What you would do is you would do categorical sort of one-hot representations of cat 0, cat 1, cat 2, cat 3, cat 4. But this isn't really practical if your categorical variable has a very large cardinality, which basically just means there's a lot of different class values, right? So if it's like last names, right? So instead, what you can do is basically apply the same analogy of Word2Vec, and now your target variable is the context, right? And if you do that and you learn on this very simple trivial toy example, what you do is then in your embedding space, you can basically essentially completely separate all the categories that belong to the odd class and all the categories that belong to the even class. So why would you care and why would you do this? Because a traditional machine learning model, if you had categorical variables, what you would typically do is you would one-hot encode them, then sort of concatenate them with the rest of your continuous features, and then you would train your model, right? So if you have a feature like gender or even country, there's only like a finite number of categories. So even if you had to make 150 categories for countries, okay, that's 150 extra columns. I can deal with that. But for really high cardinalities like postal codes or like the first three numbers of a phone number, then that's much more difficult. And that's when you can sort of really leverage embedding features. So essentially you're doing a compression. You're taking your cardinality of say like 10,000 and bringing it down to 100 embedding features, and then you're training it on that. And if you do this, you can learn much richer structure and representations than you could if you just did one-hot encoding. So this isn't a real-life example. This was actually from a Kaggle competition where they try to predict store sales in Germany. It's like something like a Walgreens of Germany, based on a bunch of features. Some of them are categorical, some of them are continuous. But one of the categoricals was what is the federal state that the store was located in. And then if you learn those embeddings and then you plotted them on a graph, so this is a two-dimensional representation of those actual embeddings, which were in higher dimensions. What you will find is the embeddings will literally be learned in such a way that you can actually see internal structure, right? You would get all the states that were part of former East Germany on one side, all the ones that are in West Germany on the other side, and states like Berlin would be on top of states like Baden, which is in southern Germany, right? So that's kind of crazy. You would not get this by doing frequency counting, by doing one-hot encoding. You would never pick up this kind of hidden structure. And the reason this happens is because all these stores, they have geographical similarities, right? So the sales, sort of the revenue of these stores in East Germany have a very different sort of profile or feature profile compared to the stores in West Germany because people buy differently, and that shows up in something like an embedding layer. So that was the sort of like traditional way, which is like, if you wanted to just directly leverage, you could train a embedding model on sort of your categorical variables and fuse it with your other additional continuous variables and then train your sort of traditional machine learning like a random forest or a decision tree on it. But what you would like to ultimately get to is sort of like a fully end-to-end learning. So this is called wide and deep learning for recommender systems. This is the model that powers Google Play Store app recommendations. And this was built at Google. And the idea is that you have a logistic regression component, which is composed of all your features that are continuous. So this could be like, how long do you stay, how far down do you scroll on like an app page, or how long you dwelled on a particular application app you clicked on. And then you have your categorical features, such as like what kind of phone you're using. And then the continuous features go through what's called a wide model. So if you only had continuous features, you can learn a model, a traditional logistic model like this, to do product recommendations. If you only had your categorical variables, you would push them, you would learn these embeddings, and then you would train a deep neural network and do your product recommendations. Their sort of innovation was that they just fused the two together and trained them jointly so that your categorical variables go through a deep layer, your continuous variables go through a shallow logistic layer that's wide, and then you fuse the entire apparatus in the top and then sort of training end to end. And this gave them something like a 4%, I think 5% lift, which from the point of view like revenue on Google Play is like hundreds of millions of dollars. So this is kind of like the end sort of penultimate sort of like model you can sort of train where it's just fully end-to-end and learned. So hopefully, by the end of this, I sort of convinced you that vector embedding is something that is actively used throughout industry. It's a very powerful technique, and it's relatively new. So just to summarize, you can learn hidden structure between entities in an unsupervised way, as in between, say, like words in a book, right? Depending on what book you sort of train your model on, you may actually learn different similarity between words. But there's applications once you sort of like go beyond the idea and you think of words as generally just being nodes that are connected in a graph, and then you can transplant that idea to any sort of data that you could model as a graph. Then you can extend that idea to sort of any kind of graphically transformable data. And then sort of the sky is the limit at that point, because you could do very, very, very unique and very creative things. You could then, in addition, leverage it as part of a supervised learning model to basically incorporate very high cardinality categorical variables, which you otherwise might have sort of computational or limitations to sort of working with. And nowadays, I think the APIs have gotten so advanced that I think it's very accessible to a wide audience. So this is like a couple of like open source APIs you can sort of work with, but I'll leave that up. But that's sort of the end of the show. Thanks for listening. Hey.
So what are the limitations of Word2Vec?
Limitations to Word2Vec. Computing. So if you don't have a GPU, it could rapidly become very intensive to train these models. I think that's a big limitation. It's very intensive to train them on CPUs. Although if you use Gensim, they have a pretty nice implementation that trains fairly reasonably fast on CPUs. And then the other limitation I would say is sort of validation, especially if you're training like a Word2Vec model, say, for the purposes of building a thesaurus, for doing search optimization, like in the example I showed. The question is, how do you evaluate how good your synonyms are, right? So it's very hard to do that without having essentially humans, like using a mechanical Turk, like you would, randomly pick 100 words, get the top 5 most similar words according to Word2Vec, and just basically have humans rank them. So that is also very important. The third is sort of the interpretability of your model, right? So you can imagine like if your model was some kind of like life critical, it was like diagnosing people for cancer, and a large part of your feature space is these categorical variables that you have embedded and then pass through sort of like a deep neural network, like here. from a regulatory and sort of legal perspective, also ethical perspective, it might not be good enough to say, your chance of cancer is 78% because my deep neural network said so, right? Because it's not as interpretable in the same way as, say, like a decision tree, which you can very obviously see what's going on.
But also, like for type of sentences, you could have like a very long sentence where the context of words at the beginning is related to one at the end. So can Word2Vec capture this, or you need
It would
other models?
So the other thing you have to, so I think this example was a little maybe misleading here, right? Because you sort of thought that the context began at duh, right? But this is just because we just ripped a sentence out of a page. Actually, the context would begin at the end of the previous sentence. So this kind of like truncation would only happen at the very top, the very top and the very bottom of a document. So if you had, so typically, so in your case, right, if you had a long sentence where he was talking about one thing at the beginning and talking about another thing at the end, right, then your context at the beginning is not going to capture at the end, right? But maybe the context of the following sentence right at the start will capture that. So because typically kind of depends, like your sentences kind of are linked, and the logic flows from one to another, right? So that may be a way you could do that. But it's very sensitive to what your corpus is, right? So obviously, if I write a bunch of sentences that individually make sense but don't make sense one after another, then I'm not going to learn, appropriate embeddings. So it's always in the data, yeah.
Would this make sense if your corpus was made up of a lot of very short documents? So large corpus, but short, like
Yeah.
tweets.
So this question is like, if you don't really have words, but your words aren't long enough, you don't have enough words to make up like an actual document, you're somewhere between words and documents, kind of like short phrases. So that actually is like very challenging. It's very hard to do similarity between short phrases or sentences. There's other sort of like architectures that will do that for you, so like in sequence-to-sequence models. But you could try Doc2Vec, but I haven't had much success with it. Hey, yeah.
Hi. Can you leverage like existing vector embeddings as sort of like a pre-trained embedding, and then for a different corpus, you use them as initialization and sort of like a transfer learning sort of way?
Absolutely you can. So Google has, I think, a Word2Vec embedding, like a pre-trained model on a huge amount of index search pages, right? And oftentimes you could just literally just use that and don't even try to train your own model, right? Or B, you start with that, you initialize your weights, instead of randomly, you initialize with Google's weights. And then you train that because they just had much more computational resource than you use. Absolutely, that's not even just for Word2Vec, any kind of like deep learning model.
So you mentioned that Word2Vec is bad at providing interpretation. So if you want interpretation, what do you use?
No. So Word2Vec, I don't think so. I more meant like these generally deep models. These deep models, especially the ones on this part, these don't have very high interpretability. Word2Vec, I think, it's fairly interpretable. I mean, you get a word, you get another word out, you see whether or not they make sense, right? But in these kind of like deep models, once you start going in this direction, like for instance, if one day in Google Play Store I get recommended Angry Bird first, and then I wanted to know, I asked Google, why did you recommend me Angry Bird? That may be hard to figure out because there's a very complicated sort of layers of non-linear processes that got you to why you got Angry Bird. It's no longer as simple as like in a decision tree where you could say, well, it's because you clicked on Angry Bird last night or something. Yeah.
So practically, what kind of problems do you use this technique on?
So one of the things, so actually just very similar to a lot of what I talk here. I actually gave this talk once internally, but then for the public talk, I just basically swapped out internal data for public data. So actually very similar. So this model here was something I built at my previous position in New York City, where it was a search engine. This was for in the IT consulting business, where they had a search engine essentially for clients, and what they did was that for each search, they basically had query expansion. At the time, they were using handcrafted lists. So they had a team of analysts who would look at certain key terms that you would search for, and then they would come up with synonyms manually and then curate them over some kind of like cadence or life cycle. And then we just realized that instead we could just take all the documents that any particular person can search for. There was like about 100,000, this was a research company, documents in their corpus, so essentially like a mini Wikipedia, and then train a word-to-vector dictionary on that, and then just use that instead to supplement the human effort, and you can easily cut, head count in that way. Not literally cut head count. They went to work on other things, but
Thank you.
Are you aware of any attempts to combine like these statistical methods with classical artificial intelligence based on logic?
classical artificial intelligence.
So the classical artificial intelligence is based on rules or considering the structure of the sentence,
Oh,
lexicography
yeah.
and logic, yeah.
I think depending on the use case, this is basically totally superseded that. So for things like, okay, so for like kind of like traditional annotation tasks, like part of speech tagging, or so for part of speech tagging in particular, like basically you have a sentence, figure out like what are the grammatical parts of speech. That's a verb, that's an adverb, that's a noun. That's already very good using traditional methods. And there's really no point in applying any kind of like deep learning neural networks, right? I think for like sort of like thesaurus building and synonyms, this is basically better than anything else out there as far as I know. Then for other kind of tasks, which I'm less familiar, so there's kind of things like name entity recognition, basically figuring out that Barack Obama in a sentence is a person and sort of like Harvey's is a restaurant. There's kind of like fusions and applications from both sort of like traditional models and some deep learning models. But gradually, I would say like overall, deep learning is slowly taking over everything because of the amount of data that you have available. But that being said, that's only if you have that data available, right? And the thing is that data is typically monopolized in a few very select companies or places, right? So, but yeah, so it kind of like depends on it's very like devils in the details kind of thing, specifically what you're talking about.
No more questions. I think we'll end here. Thank you for that very informative presentation. And we'll be sticking around, so feel free to mingle afterwards. Thank you.
Thanks, guys.